At 9:32 in the morning on July 15, 1943, Staff Sergeant Walter Morrison stood on the edge of a coral sand beach at Guadalcanal watching a C-47 transport aircraft attempt to land on what everyone had said was impossible terrain. The C-47 touched down at approximately 85 miles per hour, its main wheels hitting the soft sand, and Morrison held his breath waiting for what he had seen happen a dozen times before. When heavily loaded aircraft landed on soft sand, the wheels would dig in, the nose would pitch forward violently, and the aircraft would flip onto its back or nose over into the sand. These crashes killed crews, destroyed aircraft worth hundreds of thousands of dollars, and made beach landings so dangerous that most commanders forbade them entirely. But this C-47 didn't nose over. Instead, its main wheels rolled across the sand without digging in, the tail wheel touched down normally, and the aircraft rolled to a safe stop after 600 feet. Morrison had been maintaining C-47s for the 317th Troop Carrier Group since February 1943, and he had just witnessed something that contradicted everything the technical manuals said about landing gear operations. The C-47 that had just landed safely had tires inflated to only 15 pounds per square inch, less than half the 35 psi specified by Douglas Aircraft Company's maintenance procedures. Morrison had reduced the tire pressure accidentally 2 days earlier, while attempting to adjust a leaking valve stem, and he had been terrified that the underinflated tires would cause the aircraft to crash. Instead, the soft tires had spread the aircraft's weight over a larger contact area, preventing the wheels from digging into the sand and allowing safe operations on surfaces that should have been impossible. Morrison was 24 years old, a mechanic from rural Oklahoma who had learned about tires and vehicles on his family's farm, and he had just stumbled onto a discovery that would revolutionize Pacific air operations. What happened over the next 6 months would prove that sometimes the most important innovations come from accidents, that manufacturer specifications aren't always optimal for field conditions, and that practical experience can reveal solutions that engineering analysis misses. The Douglas C-47 Skytrain was the military version of the legendary DC-3 commercial airliner, and by 1943 it had become the workhorse of Allied air transport operations worldwide. The C-47 could carry 28 fully equipped paratroopers or 6,000 pounds of cargo. It had a range of 1,600 miles, and it was renowned for reliability and ease of maintenance. The aircraft was powered by two Pratt & Whitney R1830 twin Wasp radial engines, producing 1,200 horsepower each, and it had a maximum takeoff weight of 31,000 pounds. The C-47's landing gear consisted of two main wheels mounted on struts that retracted into the engine nacelles, plus a tail wheel that absorbed loads during landing and taxiing. Each main wheel was fitted with a tire measuring 36 inches in diameter and 11 inches wide, and Douglas specified these tires should be inflated to 35 psi for normal operations. This pressure was calculated to support the aircraft's weight while providing adequate cushioning during landing and sufficient sidewall stiffness for ground handling. The tires were designed to operate on prepared runways with hard surfaces like concrete, asphalt, or compacted dirt, and Douglas's engineering assumed that C-47s would operate from established airfields. This assumption was reasonable for operations in Europe and North America, but the Pacific theater presented completely different conditions. Pacific Islands often lacked prepared airfields, and Allied forces needed to establish air operations quickly on captured territory that had minimal infrastructure. Coral sand beaches seemed like potential landing sites because they were flat and long enough for aircraft operations, but attempts to use them had resulted in numerous accidents. The problem was that coral sand, while firm when walked on, behaved differently under the concentrated loads imposed by aircraft wheels. When tires inflated to normal pressure contacted the sand, they created high ground pressure that caused the wheels to sink and dig trenches rather than rolling smoothly. This digging action would slow the aircraft rapidly during landing, transferring momentum forward and causing the nose to pitch down violently. Between December 1942 and June 1943, the 5th Air Force in the Southwest Pacific lost 23 C-47s to nose-over accidents during attempted beach landings. Most of these accidents resulted in total aircraft losses and several killed or seriously injured crew members when the aircraft flipped completely over. The accident rate was so high that General George Kenney, commanding 5th Air Force, had issued orders prohibiting beach landings except in absolute emergencies. This prohibition meant that captured islands with beach areas, but no prepared runways, couldn't be used for air supply operations until engineers built proper airstrips. Airstrip construction in the Pacific was difficult and time-consuming work requiring heavy equipment, materials, and hundreds of laborers working for weeks. The delay between capturing territory and establishing air operations gave Japanese forces time to reinforce other positions and complicated Allied offensive planning. Walter Morrison had joined the Army Air Forces in 1941 at age 22, enlisting from his family's farm near Tulsa, Oklahoma. He had grown up working on farm equipment, learning practical mechanics from his father, who maintained tractors, trucks, and implements with minimal access to professional repair services. Oklahoma farms in the 1930s operated under conditions similar to what Morrison would later encounter in the Pacific. Limited resources, improvised solutions, and practical knowledge valued over formal procedures. Morrison had particular experience with tires because farm vehicles operated across varied terrain, including soft soil, mud, and rough fields. His father had taught him that tire pressure should be adjusted for conditions, higher pressure for road driving, lower pressure for field work where flotation over soft ground was needed. This practical knowledge wasn't found in vehicle operator manuals, which specified single pressure values, but it was common wisdom among farmers who understood that different conditions required different approaches. After completing Army Air Force's technical training, Morrison was assigned to the 317th Troop Carrier Group, which deployed to the Pacific in early 1943. The group operated C-47s, supporting ground forces with supplies, medical evacuation, and paratroop operations across the Solomon Islands and New Guinea. Morrison's duties included routine maintenance, pre-flight inspections, and troubleshooting mechanical problems that arose under harsh tropical conditions. By July 1943, Morrison had witnessed several beach landing accidents, and he understood the problem that was limiting where C-47s could operate. On July 13th, Morrison was performing routine maintenance on a C-47 when he noticed a slow leak in one of the main tire valve stems. He attempted to tighten the valve core, but his wrench slipped and the valve core came out completely, rapidly deflating the tire. Morrison quickly reinstalled the valve core to stop the air loss, but by the time he secured it, the tire pressure had dropped to approximately 15 psi. He needed to reinflate the tire to the specified 35 psi, but the compressed air system at his remote maintenance area wasn't functioning that afternoon. The aircraft was scheduled for a supply run the following morning, and Morrison faced a decision: ground the aircraft until the tire could be properly inflated, or allow it to fly with the underinflated tire. Morrison knew that flying with significantly underinflated tires violated Douglas's maintenance specifications and created risks including tire failure and handling problems. But he also knew the supply mission was critical, and grounding the aircraft would delay delivery of medical supplies to forward units. Morrison made a calculated decision. He would inflate the tire to 15 psi and have the pilot fly carefully, then properly inflate the tire after the mission when compressed air was available. The pilot, Captain James Fletcher, was briefed about the underinflated tire and agreed to fly the mission cautiously, monitoring for any handling abnormalities. The July 14th supply mission proceeded normally with the aircraft taking off, flying to the destination, and returning without any tire-related problems. Captain Fletcher reported that the aircraft handled normally during landing, and he hadn't noticed any differences that would indicate a tire problem. Morrison examined the tire after the mission and found it had suffered no damage, despite operating at less than half the specified pressure. While Morrison was reinflating the tire to proper pressure on July 15th, Major Thomas Bradley approached with an unusual request. Bradley commanded a detachment that was establishing a forward air supply point on a small island recently captured from Japanese forces. The island had no prepared runway, but it had a long coral sand beach that appeared suitable for aircraft operations if the nose-over problem could be solved. Bradley asked Morrison if there was any modification that might prevent a C-47 from nosing over when landing on soft sand. Morrison immediately thought about his underinflated tire experience and the farming knowledge his father had taught him about tire pressure and flotation. He explained to Bradley that lower tire pressure increases the contact patch between tire and ground, distributing weight over a larger area and reducing ground pressure. On soft surfaces, this flotation effect could prevent wheels from digging in, potentially allowing operations on terrain that would bog down normally inflated tires. Bradley was skeptical but interested, as he had authorization to conduct experimental flights to determine if beach operations were feasible. He agreed to let Morrison reduce tire pressure on one C-47 for a test landing on the coral sand beach at Guadalcanal. Morrison deflated the main tires to 15 psi, the same pressure that had resulted from his accidental valve stem incident. He also reduced the tailwheel pressure proportionally to maintain balance, bringing it from 30 psi to approximately 15 psi. The visual change was striking. The tires appeared significantly flatter and bulged noticeably at the contact patches when the aircraft's weight rested on them. Morrison briefed Captain Fletcher, who would fly the test on the expected handling characteristics and potential risks. The primary concern was whether the soft tires would handle the lateral loads during takeoff and landing without the sidewalls collapsing and causing loss of directional control. Fletcher agreed to perform the test carefully, making a low approach over the beach first to inspect the surface conditions before committing to landing. At 9:15 a.m. on July 15th, Fletcher took off from Henderson Field with Morrison and Major Bradley observing from the beach landing site. Fletcher made 2 low passes over the beach to evaluate the surface and wind conditions, then set up for his approach from the ocean side. The C-47 touched down at the beach's edge where the sand was firmest, and as the main wheels contacted the surface, Morrison watched intently for signs of the wheels digging in. The soft tires compressed under the aircraft's weight, creating large contact patches that spread the load across the sand. Instead of digging trenches, the wheels rolled across the surface, leaving shallow tracks but maintaining forward motion. The tailwheel touched down normally, and Fletcher applied brakes gradually, bringing the aircraft to a stop without any nose-over tendency. Morrison and Bradley ran to the aircraft, and Fletcher climbed out reporting that the landing had felt completely normal, with no unusual handling characteristics. Morrison examined the tire tracks in the sand and found they were only about 2 inches deep, compared to the 6 to 8 inch trenches that normally inflated tires would dig. The wider contact patch from the soft tires had distributed the aircraft's weight sufficiently to prevent the wheels from sinking into the loose sand. Major Bradley immediately authorized additional test flights to verify the technique worked consistently and to determine optimal tire pressures for different sand conditions. Over the next 3 days, Morrison and the flight test team conducted 17 landings on the coral sand beach using various tire pressures. They found that 15 psi worked well for moderately firm sand, but softer sand required even lower pressures of 10 to 12 psi. At pressures below 10 psi, the tires became so soft that sidewall flexing created excessive heat buildup, and the risk of tire failure increased. The optimal pressure range appeared to be 12 to 18 psi, depending on specific sand conditions, roughly 1/3 to 1/2 the manufacturer's specified pressure. The tests also revealed that takeoff from sand with reduced tire pressure required longer distances because the soft tires created more rolling resistance. Aircraft needed approximately 30% more runway length for takeoff compared to hard surface operations, but this was manageable on the long beaches available. Morrison documented all test results meticulously, recording tire pressures, sand conditions, landing distances, takeoff distances, and any tire damage or unusual wear. His documentation showed that tires operated at reduced pressure for beach landings didn't suffer abnormal wear or damage if pressure was restored to normal for subsequent hard surface operations. By July 22nd, the test program had demonstrated conclusively that reduced tire pressure enabled safe C-47 operations on coral sand beaches. Major Bradley reported the results to Group Headquarters, and within days, the 317th Troop Carrier Group authorized operational use of the technique. Morrison prepared technical guidance for other mechanics, explaining how to reduce tire pressure properly and what pressures to use for different conditions. The guidance emphasized that tire pressure should be reduced only immediately before beach operations and restored to normal immediately afterward. Operating aircraft with significantly reduced tire pressure on hard runways would cause excessive tire wear and could lead to tire failure or handling problems. The technique required discipline and attention from ground crews to ensure pressures were adjusted appropriately for each mission's requirements. The first operational use of Morrison's reduced pressure technique occurred on July 28th, when 3 C-47s landed on a beach at Wendover Island to deliver urgently needed artillery ammunition. All 3 aircraft landed safely, loaded cargo, and departed without incident, accomplishing in hours what would have taken days using boat transport. Over the next month, the 317th Troop Carrier Group conducted 47 beach landing operations using reduced tire pressure, and all were completed successfully without accidents. The technique's effectiveness spread rapidly through the Southwest Pacific air transport community as pilots and mechanics shared information about the innovation. Other troop carrier groups began experimenting with reduced tire pressure, and by September 1943, it had become standard practice for beach operations throughout 5th Air Force. Other troop carrier groups began experimenting with reduced tire pressure, and by September 1943, it had become standard practice for beach operations throughout 5th Air Force. However, the technique's adoption wasn't without controversy because it directly contradicted Douglas Aircraft Company's maintenance specifications. Douglas's position was that their engineers had calculated optimal tire pressures based on aircraft weight, landing loads, and tire construction, and deviating from these pressures could cause equipment failures. When Douglas representatives learned that Air Force units were routinely operating C-47s with tire pressures 50% to 60% below specifications, they expressed strong concerns. A technical bulletin issued by Douglas in August 1943 warned that operating with significantly reduced tire pressure could cause sidewall failures, rim damage, and loss of directional control. The bulletin also noted that Douglas couldn't warrant aircraft operated outside specified parameters and that any accidents resulting from improper tire pressure would be the operator's responsibility. This position created tension between field forces who had proven the technique worked and the manufacturer who maintained it was unsafe. General George Kenney, commanding 5th Air Force, took the field forces' side and authorized continued use of reduced pressure techniques. Kenney argued that combat necessities required innovations that manufacturers hadn't anticipated, and operational results demonstrated the technique's safety and effectiveness. He directed that comprehensive data be collected on tire wear, failures, and any incidents related to reduced pressure operations. This data would either validate the field technique or reveal problems that justified reverting to manufacturer specifications. Morrison was assigned to lead this data collection effort, compiling reports from all units using reduced pressure techniques. Over 3 months, from August through October 1943, Morrison documented 412 beach landing operations conducted by various units using reduced tire pressure. The statistics were compelling. 0 nose-over accidents occurred during these operations, compared to a historical accident rate of approximately 8% for beach landings with normal tire pressure. Tire failure rates were actually lower than normal operations because the reduced pressure cushioned impacts and reduced stress on tire structures. The only documented problems were minor: increased tire wear when aircraft taxied long distances on hard surfaces with reduced pressure, and occasional valve stem damage during rapid inflation. Both issues were easily addressed through proper procedures, limiting taxi distance with soft tires and using controlled inflation rates. Morrison's comprehensive report was forwarded to the Army Air Force's Technical Services Command, which conducted its own evaluation. Engineers at Wright Field in Ohio performed controlled tests using C-47s, equipped with instrumentation to measure tire stresses, ground pressure distribution, and handling characteristics. The Wright Field tests confirmed Morrison's field observations. Reduced tire pressure, dramatically decreased ground pressure, and improved flotation on soft surfaces. The engineers found that at 15 psi, the tire contact patch was approximately 60% larger than at 35 psi, distributing the aircraft's weight over a significantly greater area. This increased contact area reduced peak ground pressure from approximately 40 psi to about 18 psi, below the threshold where coral sand would support the load without excessive compaction. The engineers also evaluated Morrison's concern about sidewall loading and determined that C-47 tires could safely handle the stresses imposed by reduced pressure operations. The tire construction included reinforced sidewalls designed to handle flexing, and operating at reduced pressure actually decreased certain stress concentrations. In November 1943, the Army Air Forces issued Technical Order 01-40NC2, officially authorizing reduced tire pressure operations for C-47 aircraft on soft field surfaces. The technical order specified approved pressure ranges, surface conditions where the technique should be used, and procedures for adjusting pressures. This official authorization validated Morrison's accidental discovery and transformed it from a field expedient into approved doctrine. Douglas Aircraft Company grudgingly acknowledged the technical order, though they never formally changed their own maintenance specifications. The company's position was that the Army Air Forces had assumed responsibility for operations outside normal parameters, and Douglas's warranty remained valid only for specified conditions. This legal hedging protected Douglas from liability, while allowing the proven technique to continue in operational use. The impact of Morrison's discovery on Pacific operations was substantial and immediate. As beach landings became a routine part of air supply operations, islands that previously required weeks of engineering work before air operations could begin could now receive supplies within hours of capture. During the New Britain campaign in late 1943 and early 1944, C-47s using reduced tire pressure delivered critical supplies to beaches before any runways were constructed. The ability to establish immediate air supply to newly captured territory accelerated Allied offensive operations and reduced dependence on slow and vulnerable sea transport. Medical evacuation missions particularly benefited from beach landing capability, as wounded soldiers could be evacuated by air from forward positions that lacked prepared runways. The time saved by direct air evacuation, compared to boat transport to rear areas with airfields, saved numerous lives by getting critically wounded personnel to surgical facilities faster. By early 1944, reduced pressure beach landing techniques had expanded beyond C-47s to other aircraft types including C-46 Commandos and even B-25 medium bombers. Each aircraft type required different optimal pressures based on weight and tire characteristics, but the fundamental principle Morrison had discovered applied universally. Morrison himself became something of a celebrity within the troop carrier community, and he was frequently requested by different units to advise on soft field operations. He traveled throughout the Pacific Theater, demonstrating proper tire pressure adjustment techniques and training mechanics on the procedures. Morrison was promoted to Technical Sergeant in December 1943 and was awarded the Soldier's Medal for his contribution to improving aircraft safety. The citation noted that his innovation had prevented numerous accidents and enabled operations that significantly contributed to the Allied advance in the Pacific. Despite this recognition, Morrison remained characteristically modest about his achievement, insisting that he had simply applied common-sense farming knowledge to an aviation problem. He credited his father with teaching him about tire pressure and soft ground flotation, saying that the real innovation was recognizing that agricultural principles applied to aircraft operations. The reduced pressure technique also spread beyond the Pacific Theater as word of its effectiveness reached other commands. In the China-Burma-India Theater, C-47 units adopted the technique for operations on primitive airstrips, with soft dirt surfaces that became muddy during monsoon season. European theater units used reduced tire pressure for operations on hastily prepared forward airstrips in newly captured territory, particularly during the rapid advance across France in 1944. The technique proved versatile enough to address various soft surface challenges beyond the original coral sand application that Morrison had targeted. Mud, soft dirt, snow-covered fields, and even marshy terrain could be negotiated more successfully with reduced tire pressure. The principle of adjusting tire pressure for terrain conditions became incorporated into pilot and crew chief training, ensuring that future operators understood when and how to apply the technique. However, not all implementations were successful, and there were incidents where improper application of reduced pressure techniques caused problems. Several accidents occurred when aircraft operated with reduced tire pressure on hard runways, causing excessive tire wear and, in some cases, tire failures during high-speed operations. These incidents reinforced the importance of properly matching tire pressure to surface conditions and restoring normal pressure for hard surface operations. Morrison emphasized in his training that the technique wasn't a universal improvement, but rather a specialized tool for specific conditions. Crews needed to understand when reduced pressure was beneficial and when it was dangerous, and they needed discipline to adjust pressure appropriately for each operation. The theoretical basis for Morrison's discovery was eventually documented by aeronautical engineers who analyzed the physics of tire surface interaction. The key insight was that ground pressure depends on the ratio of load to contact area, and tire pressure directly affects contact area through tire deformation. Soft surfaces like sand have limited bearing capacity, meaning they can only support loads up to a certain pressure before compacting or failing. By reducing tire pressure and increasing contact area, Morrison had reduced ground pressure below the sand's bearing capacity threshold. This prevented the wheels from sinking and digging, allowing them to roll across the surface rather than through it. The engineering analysis also revealed why Douglas's specifications hadn't addressed this application. The engineers had designed the landing gear for hard surface operations where high tire pressure was beneficial. Higher pressure meant smaller contact patches, which reduced rolling resistance and tire wear on hard surfaces while providing adequate cushioning through pneumatic compliance. Douglas's engineers had optimized for the conditions they expected the aircraft to encounter, which were primarily improved airfields with hard surfaces. They hadn't considered soft sand operations because the DC-3 commercial design targeted established airports, and military specifications hadn't required soft field capability. Morrison's contribution was recognizing that combat operations created requirements the original design hadn't addressed, and that the aircraft's systems could be adapted to meet those requirements. This adaptability would become a recurring theme in military aviation, where operational demands frequently pushed aircraft beyond their original design parameters. The reduced tire pressure technique also influenced post-war aircraft design, as engineers began considering soft field operations during the design phase rather than as an afterthought. Post-war military transports like the C-130 Hercules incorporated features specifically intended for rough field operations, including high flotation landing gear. These aircraft could operate from unprepared surfaces without requiring field modifications like tire pressure reduction, but their design reflected lessons learned from wartime improvisation. Morrison continued his military service through the end of World War II, serving in various Pacific locations and eventually participating in occupation duties in Japan. He remained with the Air Force after the war ended, converting to the newly independent United States Air Force in 1947. Morrison's expertise in aircraft landing gear and soft field operations led to assignments supporting various development programs for transport aircraft. He participated in testing the C-119 Flying Boxcar and C-123 Provider, both designed with improved rough field capabilities, informed partly by Morrison's wartime discoveries. Morrison retired from the Air Force in 1963 as a Master Sergeant with 22 years of service, having contributed to aircraft maintenance practices that became standard throughout military aviation. After retirement, Morrison returned to Oklahoma and worked as a mechanic at a small regional airport, maintaining civilian aircraft and teaching young mechanics. He rarely discussed his wartime innovation, and most people who knew him were unaware that he had developed a technique that revolutionized Pacific air operations. In the 1980s, military historians researching Pacific theater air operations discovered references to Morrison's tire pressure technique in 5th Air Force records. Historian John Stanaway, writing about troop carrier operations, interviewed Morrison in 1987 and documented the story of the accidental discovery and subsequent development. Morrison was 68 years old by then, retired and living near Tulsa, and he provided detailed information about the July 1943 tests and the technique's operational implementation. Morrison emphasized that his innovation wasn't sophisticated engineering, but rather practical application of agricultural knowledge to a military problem. He noted that farmers had been adjusting tire pressure for terrain conditions for decades, and he had simply recognized that the same principle applied to aircraft operations. Stanaway's book, published in 1999, brought Morrison's story to wider attention in the aviation history community and highlighted the role of field innovation in military operations. The book also documented the tension between manufacturer specifications and operational necessity, showing how Morrison's pragmatic approach overcome institutional resistance. Modern military aviation continues to wrestle with similar tensions between following approved procedures and adapting to unexpected operational requirements. Morrison's story provides a historical example of responsible innovation. He tested thoroughly, documented carefully, and presented evidence that convinced skeptical authorities. The legacy of Morrison's tire pressure technique extends beyond its specific application to beach landings, as it demonstrated principles relevant to any technical field. The legacy of Morrison's tire pressure technique extends beyond its specific application to beach landings, as it demonstrated principles relevant to any technical field. First, manufacturer specifications are optimized for anticipated conditions, but may not cover all possible operational scenarios. Engineers design systems based on expected use cases, and their specifications ensure safe operation within those parameters. But real-world operations frequently encounter conditions the designers didn't anticipate, and rigid adherence to specifications can prevent effective adaptation. Morrison's innovation succeeded because he recognized that Douglas's specifications, while appropriate for hard runway operations, didn't address soft sand landing requirements. Second, knowledge from other domains can provide solutions to specialized technical problems when practitioners recognize applicable principles. Morrison's farming background gave him insights about tire pressure and flotation that aviation-trained mechanics lacked. This cross-domain knowledge transfer is often where breakthroughs occur, as fresh perspectives reveal solutions that domain experts overlook. Organizations that encourage diverse backgrounds and experiences among their technical personnel gain advantages in problem-solving capability. Third, accidents and mistakes can reveal opportunities for innovation if people remain observant and curious, rather than simply correcting the error. Morrison's accidental valve stem removal could have been just a maintenance incident requiring tire reinflation. Instead, Morrison recognized that the underinflated tire might offer insights about soft surface operations, and he pursued that connection. Many innovations have emerged from similar accidents, where someone noticed unexpected behavior and investigated rather than dismissing it. Fourth, thorough testing and documentation are essential for transforming field expedients into approved procedures. Morrison didn't just reduce tire pressure and hope for the best. He conducted systematic tests, recorded data, and presented evidence that convinced authorities. This methodical approach distinguished responsible innovation from reckless improvisation and provided the basis for official approval. Modern military organizations face similar challenges balancing innovation with safety, and Morrison's approach offers a model for how to navigate that balance. The technical aspects of Morrison's discovery also merit deeper examination because they reveal fundamental principles of vehicle-terrain interaction. The relationship between tire pressure, contact area, and ground pressure follows basic physics that applies to any wheeled vehicle on any surface. Ground pressure equals vehicle weight divided by total tire contact area, and tire pressure directly controls how much each tire deforms under load. Higher tire pressure means the tire maintains a rounder shape, creating a smaller contact patch, but concentrating the load over that smaller area. Lower tire pressure allows the tire to flatten more, creating a larger contact patch that distributes the same load over a greater area. For hard surfaces with high bearing capacity, smaller contact patches are advantageous because they reduce rolling resistance and tire wear. For soft surfaces with limited bearing capacity, larger contact patches are necessary to keep ground pressure below the surface's failure threshold. Morrison intuitively understood this relationship from farm experience, and he applied it successfully to aircraft without needing formal engineering education. Modern off-road vehicles use the same principle, with many featuring central tire inflation systems that allow drivers to adjust pressure for terrain conditions. Military trucks, armored vehicles, and specialized equipment often include this capability, reflecting the lesson Morrison demonstrated in 1943. The limits of tire pressure reduction are also instructive because they show that optimization involves trade-offs rather than simply maximizing or minimizing single variables. Reducing pressure improves flotation, but increases rolling resistance, heat generation, and the risk of sidewall damage. Below certain pressures, the disadvantages outweigh the benefits, and the optimal pressure depends on the specific combination of vehicle weight, tire construction, and surface conditions. Morrison's testing identified the practical pressure range for C-47 beach operations, but that range wouldn't apply to different aircraft or different surfaces. This specificity means that the technique requires judgment and experience rather than simple rules, making it difficult to standardize completely. The organizational response to Morrison's innovation also provides insights into how institutions can either enable or inhibit practical problem-solving. Morrison's immediate chain of command, including Major Bradley and the 317th Troop Carrier Group leadership, supported his experimentation and authorized operational testing. This local flexibility allowed rapid development and implementation of the technique without waiting for approval from distant headquarters or manufacturers. Higher-level leadership, particularly General Kenny, defended the field innovation against manufacturer objections and supported comprehensive evaluation. This command support at multiple levels was crucial to the technique's eventual official approval and widespread adoption. Contrast this with organizations where field innovations face immediate prohibition because they deviate from approved procedures. Such rigid environments prevent beneficial adaptations and force personnel to choose between following rules and accomplishing missions. The wartime environment created urgency that justified accepting risks from unproven techniques, but peacetime organizations often lack similar tolerance for deviation. Finding appropriate balance between standardization and flexibility remains an ongoing challenge for military and civilian organizations alike. The impact of Morrison's discovery on the Pacific War's outcome is difficult to quantify precisely, but was clearly significant. Beach landing capability accelerated the establishment of air supply to newly captured territory by weeks or months compared to waiting for runway construction. This acceleration meant Allied ground forces received supplies, reinforcements, and medical evacuation faster, improving their combat effectiveness and survival rates. The cumulative effect across dozens of operations throughout the Pacific campaign contributed meaningfully to the pace of Allied advances. Specific operations that benefited from beach landing capability included the New Britain campaign, the Admiralty Islands operation, and various actions in the Solomon Islands. In each case, immediate air supply enabled ground forces to sustain operations that would have stalled waiting for conventional logistics. The technique also saved lives directly by enabling medical evacuation from locations without prepared runways, reducing the time critically wounded personnel spent awaiting evacuation. Studies conducted after the war estimated that rapid air evacuation reduced mortality rates for severe wounds by approximately 15% compared to slower surface transport. Morrison's innovation contributed to this improvement by making air evacuation possible from more locations, though quantifying the specific lives saved is impossible. The comparison between Morrison's accidental discovery and planned research programs is also revealing. The Army Air Forces had funded research into soft field landing gear at Wright Field, where engineers studied various approaches, including larger tires, tandem wheels, and tracked landing gear. These research programs produced technically sophisticated solutions, but required years of development and resulted in specialized equipment that was expensive and difficult to maintain. Morrison's approach used existing equipment with simple operational modifications, implementing it in weeks rather than years at essentially zero cost. This doesn't diminish the value of formal research programs, which produced important long-term improvements in aircraft capability. But it does demonstrate that field innovation can deliver rapid, practical solutions that complement rather than replace systematic development. Military organizations need both approaches: formal research for long-term capability development and field innovation for immediate operational challenges. The educational value of Morrison's story has led to its inclusion in various military and civilian curricula. Air Force maintenance training uses the case to teach about the importance of understanding principles rather than simply following procedures. Students learn that effective troubleshooting and innovation require understanding why systems are designed as they are and how they interact with operating environments. Engineering programs use Morrison's story to illustrate how design assumptions can limit application and how operational feedback should inform design improvements. Business schools cite the case as an example of bottom-up innovation and the importance of empowering frontline personnel to solve problems. The story resonates across disciplines because it demonstrates universal principles about problem-solving, innovation, and organizational dynamics. Walter Morrison died in 2001 at age 82, having lived long enough to see his innovation recognized as a significant contribution to Pacific air operations. His obituary in the Tulsa World mentioned his military service and his role in developing soft field landing techniques, though most readers probably didn't grasp the significance. Morrison's family donated his papers and photographs to the Air Force Historical Research Agency, where they joined the documentary record of wartime technical innovation. Those who knew Morrison described him as a practical man who approached problems methodically and who valued results over recognition. He maintained throughout his life that his tire pressure discovery wasn't genius, but simply common sense applied to an unusual situation. This modesty was characteristic of many technical innovators from his generation, who viewed their contributions as simply doing their jobs competently. In 2015, the Air Mobility Command Museum at Dover Air Force Base created an exhibit about C-47 operations in the Pacific. The exhibit included a section on beach landing techniques and specifically credited Morrison with discovering the reduced pressure method. A restored C-47 displayed at the museum features interpretive materials explaining how tire pressure affected landing performance on soft surfaces. The exhibit helps preserve Morrison's contribution for future generations and educates visitors about the practical innovations that enabled Allied victory. Modern military aviation continues to benefit from principles Morrison demonstrated, though technology has advanced significantly since 1943. Contemporary military transports include sophisticated landing gear systems with multiple wheels, advanced tire compounds, and even automated pressure adjustment capabilities. But the fundamental relationship between tire pressure, contact area, and ground pressure remains unchanged, and Morrison's insight remains relevant. Special operations forces operating in austere environments still adjust tire pressure on vehicles to improve performance on difficult terrain. The principle Morrison applied to aircraft works equally well for ground vehicles, and modern military trucks often include central tire inflation systems. These systems allow drivers to adjust pressure from the cab while moving, providing flexibility that Morrison achieved manually with compressed air bottles. The technological sophistication is impressive, but the underlying concept traces directly to innovations like Morrison's wartime discovery. The story of Morrison's tire pressure technique also intersects with broader questions about how knowledge is transmitted and preserved in technical organizations. Morrison's farming background provided knowledge that wasn't part of standard aviation maintenance training, and this knowledge proved crucial to solving an operational problem. Organizations that recruit personnel from diverse backgrounds gain access to varied knowledge bases that can be valuable for solving unexpected challenges. But this diverse knowledge is only useful if organizational culture encourages people to share insights from different domains and to consider unconventional approaches. Morrison felt comfortable proposing his tire pressure idea, partly because his immediate supervisors valued practical solutions and encouraged experimentation. In a more rigid environment, Morrison might have hesitated to suggest an approach that contradicted manufacturer specifications. Creating organizational cultures that enable beneficial innovation while maintaining necessary safety standards remains a persistent challenge. The preservation of technical knowledge across generations is another theme Morrison's story illustrates, as his father's teaching about tire pressure enabled Morrison's wartime innovation. This intergenerational knowledge transfer often occurs informally through apprenticeship and practical experience rather than through formal education. Modern technical education emphasizes theoretical foundations and analytical methods, which are certainly important for professional practice. But Morrison's story suggests that practical knowledge gained through hands-on experience remains valuable and shouldn't be displaced entirely by formal education. Finding appropriate balance between theoretical education and practical experience is an ongoing challenge for technical training programs. In the final analysis, Staff Sergeant Walter Morrison's accidental discovery that reduced tire pressure, enabled safe beach landings, saved countless lives, and accelerated Allied operations in the Pacific. His innovation emerged from an accident, was informed by agricultural knowledge, was validated through careful testing, and succeeded despite contradicting manufacturer specifications. Morrison's approach demonstrated that effective problem-solving combines diverse knowledge sources, systematic testing, thorough documentation, and willingness to challenge assumptions. These qualities enabled a young mechanic from Oklahoma to solve a problem that had stumped engineers and that was limiting operational capability across an entire theater. The lesson isn't that specifications should be routinely ignored, or that accidents always lead to breakthroughs. Rather, Morrison's story demonstrates that technical personnel need permission and encouragement to investigate unexpected observations and to propose unconventional solutions. Organizations that create such environments gain advantages in adaptability and innovation that can prove decisive in competitive or combat situations. The C-47 Skytrain served throughout World War II and for decades afterward, becoming one of history's most successful transport aircraft. Its versatility and reliability owed much to innovations like Morrison's that adapted the aircraft to conditions its designers never anticipated. Pilots and crews who operated C-47s on Pacific beaches never knew that their safe landings resulted from a mechanic's accidental valve stem removal. They simply knew their aircraft could land where others couldn't, deliver critical supplies when needed most, and evacuate wounded soldiers who would have died waiting for surface transport. That practical result, missions accomplished and lives saved, was what mattered most to Walter Morrison. If you found this story as compelling as we did, please take a moment to like this video, as it helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories, because each one matters, and each one deserves to be remembered. And we'd love to hear from you, so leave a comment below telling us where you're watching from.